All right, guys, so we're going to look into now some more applications involving derivatives. If you remember correctly, we kind of talked about we wanted to make sure that we understood the more algebraic approach to derivatives before we went in and found any applications involving where derivatives are really used for, like we're going to talk about today, which we talked about in the very beginning, if you remember correctly. We described the derivative to be the slope of the tangent line, but if you remember correctly, we first talked about limits. We even said the slope of the tangent line had its own kind of special definition as well, or a little secondary definition, and that was a way for us to find the instantaneous rate of change or the speed of a certain particle moving in motion on a curve or on a line or whatever the case may have been. And so that's what we're going to look into today. So we're looking at 3.4. And 3.4 has a little dab of 3.3 in there as well too. And we're talking about velocity and rates of change. The definition we're going to look at to start some things off is if you want to find the instantaneous rate of change of a specific function f with respect to x at a value of a, all right, at a value of a in there, then we just take the derivative of that function and substitute a in for the value of x. Or a lot of times you're going to see it as a value of respect to t as well, okay? And so our instantaneous rate of change can be found by finding that derivative of our function. On the next page, I'm going to show you a little bit different here, is what you also might see. And we're going to compare a little bit about the relationships between position, velocity, and acceleration. So let's say we're talking about our three main topics here. So we have position, and we have velocity, and we have acceleration. When we're looking at these three terms, they all have a great relationship with each other. Let's start off with the first one. We normally see position being shown in terms of s of t. This shows us a position of a function, whether it is a certain point on a curve or whether it's going to be where a particle actually is at a given time on the curve itself, all right? And so when we're talking about position, the relationship between position and velocity is, well, velocity is the derivative of position. So velocity with respect to a certain timetable of t is s prime of t. Well, then now if we're talking about acceleration, its relationship between position and velocity is, well, velocity is the derivative of position, and then acceleration is going to be the derivative of velocity. And so we write that as a of t is equal to v prime of t or s double prime of t as well, okay? And so this is going to kind of take us into a few different things that we're going to be looking at, but more specifically, let's take a little gander at a very first example that we're going to look at more so in terms of the rate of change. That's what we talked about derivatives in the very beginning. So let's take a look at an example here. We want to go ahead and find the rate of change of the area of a circle with respect to its radius r, okay? And then this is evaluate the rate of change of a at r equals 5 and so on and so forth, all right? And so we're going to almost use our same kind of focus of position, velocity, and acceleration in this exact same manner. Because when we talked about the rate of change was just the derivative of the position function. Well, the derivative of the position function is velocity, and so there's a relationship there. And we can kind of see that using some past examples that we know about, all right? So first and foremost is we have to go ahead and find the rate of change of the area A of a circle. Well, what is our position function here? You got to know the area of a circle to be able to find that position function. The area of a circle, we know, is to be pi r squared, right? Area of a circle is pi r squared. And so now we use this to kind of solve that very first part of this problem, find the rate of change. Well, the rate of change, or the instantaneous rate of change with respect to r, is we need to go ahead, and I'll just kind of make this part A. We need to go ahead and find out what the derivative of a is with respect to r. Well, derivative of a with respect to r is taking our derivative of r, in this case, which would be 2 times pi r. All right? And that's about it for that. Well, there's our instantaneous rate of change. And now it says, evaluate the rate of change of the area when r is 5 and when r is 10. We'll go into our past definition. If you want to find that instantaneous, the exact spot as to where it's going to happen, we need to go ahead and substitute wherever our radius is into our derivative. So this is going to show us that, hey, if our dr is 2 pi r, and I want to know when r is equal to 5, when r is equal to 10, well then 2 pi times 5 gives us 10 pi, which we know is roughly around 31.4. And then on the other side of things, we have 2 pi times 10, which in this case is going to be 20 pi, or roughly 62.8, okay? And so the last part of this problem says, it's kind of a food for thought. It says, if r is measured in inches and a is measured in square inches, or inches squared, what units would dr be in? Well, we got to think about it for a sec. You got to kind of notice that as we're going through, the rate of change gets bigger as r gets bigger. And so obviously the bigger change in area as the circle is growing from its radius. All right? As the radius is growing, the circle is obviously growing as well too. All right? And so that means our focus is on the radius. All right? And so since the radius is making the change to the area, we are going to use the appropriate units of square inches because the radius was in square inches as well. Okay? So we got to kind of think about that, as well too. And so for every square inch of area, we have 1 inch of radius, right? So we have 1 inch of area for every All right, sorry guys, I don't know if you heard that. My dogs are going crazy. Sorry to put a little pause on that. But we were saying down at the end, all right, that we're talking about our units for it. Appropriate units for DADR are square inches of area per 1 inch of radius, okay? Now, let's take into account a little bit more so as to what we were talking about in terms of position, velocity, and our acceleration. So let's take a look at an example here. So we say the displacement in meters of a particle moving in a straight line. Particle motion, very, very, very important to know. All right, we're going to be talking about particle motion a lot. The displacement in meters of a particle moving in a straight line is given by the following equation. S is equal to 5t cubed plus 3t plus 8, where t is measured in seconds. And so it says find the velocity after t equals 2 seconds and find the acceleration of t equals 2 seconds as well. So let's take a look here. So first and foremost, we need to go ahead and find out. So we know our position, S of t, is equal to 5t cubed plus 3t plus 8. And we said that S prime of t is equal to velocity. So the velocity of t is going to be 15t squared plus 3. And now we go ahead and use part A to find out what v of 2 is. Well, v of 2 is 15 times 2 squared plus 3, which will equal 63. And so, just kind of a little side note here. Let's say they said, what is the velocity, or when is the velocity a certain value? So, what if they said, what is the velocity when it's 100? I guess. All right, we'll say, what time does this happen when the velocity is 100? And so, if they ever said, when is the velocity or the acceleration a certain time? All right, you would set 100 is equal to 15t squared plus 3. Then you'll subtract 3, divide by 15, take the square root, and find out what that t value is. Okay, so if they ever ask you, hey, when is the velocity a certain value? Well, then we can do this by this way. But kind of not going to go too far into that right now. But now let's take a look at the second part where it said acceleration. Well, acceleration is s double prime of t, which is equal to v prime of t. So v prime of t is equal to 2 times 15 is going to give us 30t. And so now we want to go ahead and find out what acceleration is at t. I'm sorry, not at t, but at 2. So at 2 seconds, our acceleration is going to be 30 times 2, or of course, at 60. All right, so there's a little kind of an insight into the relationship between position, velocity, and acceleration as well. The last thing I really kind of want to talk about here is the relationship between speed. So let's kind of review. We've said, hey, position is usually s of t. Velocity is v of t, which equals s prime of t. And then we said that acceleration is v prime of t, or a of t. So what about speed? Speed comes into play when we're talking about velocity. Speed is equal to the absolute value of velocity. We're going to be asking ourselves, well, how can velocity even be negative? Well, let's put it this way. Let's say, for instance, you're leaving your house, right? And if going in a positive motion was going away from your house, like to the store, and then maybe velocity going in the negative portion would be coming back home because you're going the same path back home in a different direction, all right? And so maybe that's kind of how you would see velocity at a negative side of things. And when we're talking about speed, think about it. If I was going to the grocery store at 40 miles an hour, if I came home at 40 miles an hour, it's not negative 40 miles an hour, it's still 40 miles an hour. And so that's kind of where we get speed from as well. All right? That's going to wrap up this lesson here today, guys. And we'll be working on the assignment to talk about position, velocity, acceleration, and all the good stuff in 3.4 first thing on Monday.